When you create a heap using insert operation, the time complexity for an array of n elements would be O of n log n. But if you create a heap using the heapify operation for the same array of elements, the time it takes has an upper bound of O of n, even though it is the same array. But how? Hello everyone. We are going to discuss heaps in this video, so it might be better to check out these two videos before watching this one if you have no idea about what heaps are. If you are already done with those, let's check out the build heap function in the context of max heaps. To understand this, we need to look at the heapify function. The heapify function works on any node and restores the heap property for that node. And since max heaps follow the property that for any node n except the root, the value of its parent is always greater than or equal to itself, the heapify function compares the parent with the child element and swaps them if the max heap property is not followed. We need to perform the heapify function recursively because it can so happen that the node with which the value is being swapped might disrupt the heap property for that node. But how do we do this? There are actually two ways of doing this. We can heapify up or we can heapify down. If you have watched my last video, you would have observed that when we inserted a node in the heap, we bubbled the inserted element upwards. This is heapify up. And when we deleted the root, we swapped the root with the last element and then we synced the root such that it goes to its place. This is heapify down. Both of them should be performed recursively until the heap property is restored for that node. Let's quickly revise both heapify up and heapify down function. In the heapify up operation, we first assume that the heap above the current node is a max heap. Then we compare the value of the current node with its parent. If the value of the parent is less than the value of the current node, we swap the two elements and perform the heapify up operation on the parent again. Since it is possible that with the last swap, the max heap property got disrupted for the heap above the parent node. We don't have to worry about the other child of the parent because it would anyways be smaller than the parent. So by extension, it would be smaller than the operated upon node if a swap is necessary. While in the heapify down operation, we first assume that both the children of the operated upon node are max heaps themselves. Then we find the largest among the three elements, the node, the left child and the right child. Then the value of the largest child is swapped with the value of the current node. But the node with which we swapped the current node might be less than its children now, thereby violating the max heap property. Hence, the heapify operation is needed for the swapped child as well. So the heapify function calls itself recursively on the swapped element and the min value sinks down the heap. The time complexity of both of them is big O of log n because in the worst case, we might have to traverse the whole height of the tree. Now coming to building a heap, we can build a max heap using the insertion operation as well. Let's look at and try to understand the following animation where we build a heap by inserting these elements one by one. Since we are using insertion to build a heap, we'll have to follow the heapify up operation because at every iteration, the end element in the array or the bottommost element in the heap is being changed. The code for this is here. We'll discuss it in a later video. We'll try to build a heap for the following input, where first we insert 10. Since we have only one node, the max heap property is being followed, but we still call the heapify on this node. Then we move on to 20 and insert it into the tree. Since a heap is a complete binary tree, we always start from the left. So we insert 20 here. Now, max heap property is not being satisfied, so we first call heapify on 20, which checks if the parent is less than itself. If yes, we swap them and call the heapify on the parent again. Now we move on to 30. Again, since we go from left to right, we insert 30 here. We then perform Heapify on 30, which checks if the parent is less than itself. If yes, it swaps the parent and the child and calls Heapify on the parent again. Now this process is pretty tiresome, so I'll play a short animation where each node is inserted one by one. Notice our call stack here. Now if you see the operations performed, when there were less than 2 nodes, we used only one recursive Heapify operation. When we had less than 4 nodes, we used 2 recursive Heapify operations. When we had less than 8 nodes, we used 3 recursive Heapify operations. And we can go on and on like this. We also need to note that this is the worst case in the terms of number of Heapify operations used, because this array is sorted in ascending order. So for each iteration, we are inserting a node which is greater than the maximum node in the heap. So each element will surely travel to the top of the tree because we are building a max heap. Now let's come to the build heap function, or the build max heap function in our case. In this function, we convert a given array directly to a heap without inserting or deleting elements from the array. So all the operations are done in place. Again, since we are clear that for any complete binary tree to be called a max heap, all the elements in the tree should follow the property that p greater than equal to c for any parent p and its child c. For that, we need to go to each element one by one and perform the Heapify up operation or the Heapify down operation. Also, we can go from top to bottom or bottom to top. So there are 4 ways in which we can build a heap. We can go top down and use Heapify up operation recursively. We can go top down and use Heapify down operation recursively. We can go bottom up and use the Heapify up operation recursively. Or we can go bottom up and use the Heapify down operation recursively. Let's look at them one by one. When we go top down and use the Heapify up operation, we are doing something similar to inserting each and every node one by one, where even if we satisfy the max heap property of a node, its child might reach the root in the worst case, leading to O of n log n time complexity. We cannot go top down and use the Heapify down operation because the Heapify down operation assumes that the subtrees rooted at the children for any node are max heaps themselves, which is not the case in this case, since we can see that this is not a max heap and this is also not a max heap for this node. When we go bottom up and use the Heapify up operation, each node can reach the root in the worst case, leading to the worst case time complexity of O of n log n again. However, when we go bottom up and use the Heapify down operation, we can avoid some work here. Let's see how. Firstly, since we are doing Heapify down operation, we don't have to do the Heapify business on the last row or the leaves of the tree. This is because single node is always a heap, and for any complete binary tree having n nodes, there are at most n by 2 leaves. Secondly, the work that we do at each node depends on the height of that node. Since at most, node can go h number of steps in the downward direction. And since in a complete binary tree, there are more nodes at the bottom of the tree than at the top, so more often than not, the heapify operation takes O of 1 time or constant time. We can also prove this mathematically. To start with that, let's say we have a node which is d level down from the root. That means the depth of the node is d. Now, the amount of time taken for any node is equal to the number of comparisons we do to restore the heap property, which for any node of height t would be equal to t, since the number of nodes below this node would be equal to t. Then for depth d, the height would be h minus d. So the total work done for any node at depth d would be h minus d. And the total number of nodes at depth d are 2 raised to d. So the total work done at any level at depth d is equal to 2 raised to d into h minus d. And to compute the total work done for the whole tree, we sum the work done at each level where d goes from 0 to h minus 1. H minus 1 because we are not considering the last level as discussed earlier. Now let k be equal to h minus d. So the equation becomes this. Since d goes from 0 to h minus 1, k would go from 1 to h. And 2 raised to h minus k can be written as 2 raised to h upon 2 raised to k, and 2 raised to h can be approximated to n, where n is the number of nodes in the heap. Approximated because the last level is never fully filled. Hence, the number of nodes could be between 2 raised to h and 2 raised to h plus 1. Hence, t of n can be approximated to summation of n by 2 raised to k into k, where k goes from 1 to h. And we can take n outside the equation because it's a constant. Now, since the infinite sum of this series converges to 2, the finite sum till h will always be less than 2. That means t of n would be less than equal to n times 2. That means t of n is of the order of big O of n, where n is the number of nodes in the heap. Thanks for watching this video. We'll try to code heaps in the next video. Also, we'll try to code the build heap function in the next video. So please subscribe to my channel to not miss the update. Also, please like this video if you learned something and subscribe to keep learning. Thank you.